Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over an exercise where we're going to find the area of a polar region between two curves. This was something we sort of know from the earlier sections of calculus, that we were trying to find the areas or area in between two curves, but we were in the rectangular coordinate system, xy coordinate system, but right now we're in the polar coordinate system, and equations are given in the polar form. So we have four hand-picked exercises for us to go through today. And let me just give you some heads up to see what kind of graphs we have in this problem. So in the first one, we have the graphs of r equals 2, 1 minus cosine theta, and the other one is 2, 1 plus cosine theta. So these are blue and purple curves here. So what we need to do to get to those graphs and find the corresponding intersection points is having the table of sample values at the left corner over there, so that you have, I sort of represented the first graph by R1 and the second one by R2, and I sort of calculated or evaluated R1 and R2 for different theta values to see what the corresponding R values are. So this is for the first problem, and please watch the rest of the video to see what I'm going to do to pinpoint those intersection points. And then the second one, again, we have two different graphs. They intersect, as far as I can see that they intersect at two different instances, two different points. So we're going to sort of try to locate them, but at the same time, we're using the table of sample values. And then the last one, we have the circle and the cardioid, and we're trying to find the area of the crescent over there. Right at the top, there's a crescent over there, so we're going to find the area of that. So let me just stop here in my introduction, because I want you to watch the rest of the video to see how we're going to obtain these graphs from scratch and write down the integration formulas to be able to come up with the areas. So this is already a long intro, I'm sorry about that, and let's get started. All right, let's start with part A. We're going to find the common, we're going to find the area of the common interior. We have two curves, so a common interior of r equals 2, 1 minus cosine theta, and r equals 2, 1 plus cosine theta. And at this moment, please have your TI-84 and start graphing these two curves. And don't forget to put it in the polar form, obviously. So what we need is, just since we have two different curves, we first need to find the intersection points to be able to pinpoint these regions. It says common interior, so you want to know exactly where this happened. Since it's a common interior, so the curves intersect, obviously. So please go ahead and graph these two curves in the same plot. And you can pause the video anytime. So, and this is what you should expect to see once you are done with the plotting. So I called the first curve to be R1 and the second one to be R2. And R1 is right here, and R2 is right here. Blue and purple curves, okay? So when it says common interior, now we can see what it is. It's exactly here. We have two different smaller inner loops, and the sum of that is the common interior. And to be able to sort of graph, to be able to find the area of the common interior, we need to pinpoint the intersection points. Now here we go. I have the intersection points happening here. I can visually see that the intersections happen at theta equals pi over 2 and 3 pi over 2. As you see that the r values are exactly the same at those points. But again, those graphs do not tell you much if you don't put the table next to that. And in fact, I was doing the table, I was making those tables in the previous videos by hand for you to see the process of constructing that. And at this moment, I just placed the table right away because I don't want to spend time on it, but you should, because this is how you find orientation and how you be comfortable to see where you start on the graph and then how the graph moves along the way, okay? For example, when theta equals 0, R1 is 0 and R2 is 4. So R1 is the blue graph. So here we start for the blue graph. We start right here. For R2, let me just also write R1 and R2 here. We start right at the edge here because R2 equals 4 at theta equals 0. Okay, and then you can see what happens at pi over 2. Both get the value of 2. So that means this guy is going to follow this path, and at theta equals pi over 2, r is going to be 2. So I can see the direction here. And then same thing is happening here. So this guy is going to go all the way to theta equals pi over 2 and hitting r equals 2 over there. Okay. So let's try to find the intersection points analytically, even though I know that one is happening here at the top here, and another one is happening here. And these correspond to pi over 2 and 3 pi over 2, as you see. But again, I want to find those analytically. All right. All I'm going to do to find intersection points is to set R1 and R2 equal. All right, let's do that. Let's just set R1 and R2 equal. Okay, so R1 equals, well, R1 is given already, so 2 times 1 minus cosine theta equals 2 times 1 plus cosine theta. Okay, and this is 2 minus 2 cosine theta equals 2 plus 2 cosine theta. And I'm going to subtract 2 from both sides. So you have negative 2 cosine theta equals 2 cosine theta. And now I'm adding 2 cosine theta to both sides. So this gives you 0 equals 4 cosine theta. And that is equivalent to cosine theta equals 0. So at this moment, you can go ahead and use your calculator to find arc cosine 0, but it's going to only spit out one value. So what you can do to find all possible theta values from 0 to 2 pi for theta, so you go back to the unit circle, and we're looking for cosine theta equals 0, so we're checking the x-coordinates of the points on the unit circle to be 0, and you can visually see where this happens. So it happens right here and right here, as you see that x-coordinates are all 0, and the corresponding angles are pi over 2 and 3 pi over 2. So we can go back and write down the solution of this trig equation to be pi over 2 and 3 pi over 2. And in fact, we already knew that pi over 2 and 3 pi over 2 would be the solutions, right? So that intersections happen at theta equals pi over 2 ray and theta equals 3 pi over 2 ray. Okay? So now, once we pinpoint the intersection points analytically and graphically, so let's consider, or let's start thinking about how we can come up with this area of the common interior. Okay? And one quick observation here is that if you check this region carefully, if you zoom in, you can see that it consists of 4 equal regions, okay? So one region is right here. So I'm going to call it 1. Second region is right here. And the third one is right here. And the fourth one is right here, okay? So the area of each region is exactly identical. Okay, so why don't we just find the area of 1 and multiply by 4? Okay, that's exactly what I'm going to do. And to be able to find the area of one of them, let's consider this one. We can consider R1 because R1, remember that R1 was starting from 0 going all the way to 2 at pi over 2. So that means we are going in this direction. So if I choose the lower limit of the area integration, 0, and the upper limit to be pi over 2, and then if I multiply that area formula for this part by 4, I can get the total area. Okay? So why don't we do that? All right, so I'm going to write the total area for common interior to be equal to 4 times the area of that little piece over there, and that is for integrating R1, which is 2 R1 squared, in fact, in the formula, from 0 to pi over 2. Okay? All right, so that's good. Let's simplify this. This is 2 times 0 pi over 2 for 1 minus cosine theta squared d theta. And I can combine 4 and 2 here, and I can write 8. And now I'm going to expand. 1 minus cosine theta quantity squared. Okay, so to save space, I'm going to write everything here. Okay, so 1 minus 2 cosine theta plus cosine squared theta d theta. Okay, and I can tell you that since this is the known trick at this moment, we are going to use the power reducing formula for cosine squared theta. I'm going to go ahead and write down or replace cosine squared theta by cosine 2 theta plus 1 divided by 2. Okay? All right, so let's just integrate all in once, okay? So we have 8. Let's look at the antiderivative right now. So theta minus 2 sine theta plus 1/4 sine 2 theta plus theta over 2. Okay? And this is from 0 to pi over 2. All right, so let's plug in the upper limit. So what do we have? 8 pi over 2, 2 sine pi over 2, right? Plus 1/4 sine pi and pi over 4. Okay, so you visually verify that if you plug in 0 for theta, okay, here, 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 and here, you get sine 0 in certain cases and 0 in other cases. So essentially this is 0. So that part, the lower limit, is going to contribute only 0. Okay? And as well, this sine pi is equal to 0 if you use your calculator. Okay? And the sine pi over 2 is equal to 1. So let's see what we're left with. Okay? So the total area is going to be equal to 8 times pi over 2 minus 2 plus pi over 4. Okay? And if you simplify this, what do you get? 6 pi minus 16. Okay? All right, so this is the total area of the common interior of R1 and R2. And to be able to find the area, we use the symmetric property together with the exact calculation of exact evaluation of the intersecting points. Okay, so and going back to here, so the total area of the common interior is going to be 6 pi minus 16. Okay, and please spend some time with this table. You can pause the video anytime and try to sort of come up with that to get the right orientation and everything. Because graphing is the first part to understand what's going on. And you can use your calculator, that's fine, but calculator helps in a limited way to be able to find the orientation and other things and intersecting points. You need to carefully analyze the graph together with the table. All right. So I think this is already a long video. I'm gonna start part B in the next video. Please continue that. Continue to my next video, and I'll see you there. Bye.